Do you see
Yeah, we see your screen.
the just is oh you see it? Okay, you don't just see the window.
It's not full screen, but almost, yeah.
Hey, Robert, how you doing? This is Jeff.
Hi, Jeff.
There's the camera back there. Hi, Everett. Thanks for your virtual participation throughout this workshop. It's been great.
Yeah, thanks for
Recording has started.
letting me join remotely. I've got a baby at home and slightly reduce my carbon impact.
Those are both good. One of them much better than the other. All right. Well, since recording's on, I think we're gonna stop the chit chat. That leaves at 0. There's a couple minutes left. As long as I know which direction it's counting. It'll be obvious as you watch. I don't think I'll have time. Yeah, no, but everybody's been great. So.
Everett? It's Mike Reagan. So is this a CDS or is it a grouped, the diff file you have on there?
I think that's CDS. It's actually ground-based, yes.
That's fine. But I mean, it's straight, just no averaging? Not grouped averaged?
No.
Okay.
I think it's a CDS pair. Been a little while. Get it.
Shall we go, or should we go fetch people, or what? Session. I'll be back in, we're gonna start in exactly.
Two minutes and we're gonna start. She tried to, and I don't know which one is when I was working.
She said if the mouse.
Yeah, but then I need to move it over here. It's too much for a Wednesday afternoon. Stuff in general. Have to be.
Alrighty, everybody. I am sorry. It turns out I have another job. It distracted me for about 5 minutes, but I'm back. I'm here for you for the rest of the day. We're gonna do our final session here. We're gonna start with Everett. So Everett, please proceed.
Okay, thank you. Should I aim to wrap up by 4:05 or 4 o'clock?
You can take the allotted time. Don't,
Okay,
I mean,
all right.
Yeah, don't worry about
Yeah.
it.
Okay, thank you. Yeah, my name is Everett Schlauer. I'm an assistant research professor at the University of Arizona. I look forward to talking about some ways to mitigate systematic noise in near-cam grids and time series, but some of these lessons can apply to pretty much all near-infrared modes. So this is in collaboration with the NearCam instrument team and the Transiting Planet Exoplanet early release. So the exoplanet community and I are interested in measuring really small signals with JWST. And maybe one of the pie in the sky ideas is detecting oceans in around terrestrial habitable worlds, but that requires exquisite precision. For example, Suisse et al. 2020 find that if the noise floor of JWST is below 3 parts per million, then it's possible to detect star planet systems with detectable oceans. If it's larger than that, then it's not. And like 3 parts per million for reference is if I give you 2 copies of Tolstoy's War and Peace and try to distinguish one word just between these 2 copies, that's what 3 parts per million. So this odyssey of JWST to maybe someday get to that level is impacted by noise monsters. There's 1/f noise, wavefront variations, visit long trends, and these are some of the systematics that we can see in exoplanet times. And just also so we're going to start with 1/f noise, but just as a reference, this is where some of the data products are at, like JWST stage 3 white light curves have areas for improvement. This is transit of the exoplanet WASP 39b, and what one of the reductions with my code t-shirt can do current precision. So this 1/f noise monster we've seen and appear in different ways. There's this horizontal banding for NearCams along the fast read direction. It's especially difficult with the GRISM time series mode because the spectrum is parallel to the fast read direction. So when you bin together wavelengths, this adds along this correlated read noise direction. So I'll just present one algorithm, the ROBA 1/f mitigation algorithm. It stands for row by row, odd even by amplifier. It's pretty simple. I think it's fairly similar to other algorithms we've seen before. The first step in this is to define a mask where you're going to use sky background pixels for 1/f subtractions. For the time series modes where you put a bright star on a specific place, you can predefine this mask because you know where the star is going to be. Step 2 is to run through the stage 1 of the pipeline up to past the super bias step, and this is a replacement for the reference pixel step. So for step 3 in this algorithm is to select a group and then do a slow read model. So in this case, it's an odd even correction for each amplifier, and then if you subtract this off, you can see most prominently the 1/f noise. So the simple way to measure this, remove the striping, is just take the medium of the row for that amplifier. I'll discuss some fancier method later. So if you put together these slow and fast read models, you can subtract this, the 1/f noise banding on that group, and then repeat this for all the groups in an integration, and proceed along the stage 1 pipeline. I think we were discussing earlier, skip the dark current step because that can add noise, and also need to usually increase the jump threshold. As I think Mike was saying, the reference files may underpredict the noise, so that the jump step tends to be overzealous in identifying noise as jumps. So the ROBA correction, cosmetically can remove these effects, and especially so the reason I do it at the group level is it can help with these odd even and amplifier offsets, especially our problem when you don't have reference pixels in a subarray. So here's the default stage 3 product, and what this 1 over f, the ROBA correction can do to bring the noise closer to the theoretical limit from photon and read noise. You can also apply ROBA and these algorithms to the GRISM spectrum. The challenging thing is there's many fewer sky pixels to use and only one amplifier on the side that has to be extrapolated. So you can only subtract the common noise between amplifiers and not the individual amplifier noise. So the benefits of doing the ROBA correction for the spectroscopic data are not as large, but it can bring you closer to the theoretical photon and noise limit. So here's an example, just using reference pixels versus doing this ROBA 1 over f correction. So but we're still a ways away from the theoretical limit. So what are some ways to maybe improve the 1 over f subtraction? I'm going to discuss an idea that came out of Team Roof. This was reduce 1 over f, a group within the Transiting Early Release Science program, to sharpen the proverbial spear against the cyclops of 1 over f noise. And one idea that came out of this was using a Gaussian process. So you can construct a kernel that sort of looks like a 1 over f noise power spectrum by putting together a bunch of terms that are not 1 over f, but if you add them together, it can sort of describe a 1 over f law in the power spectrum. And I think I haven't done any comparison. I think it ends up maybe fairly similar to NS clean, but works more in the time than Fourier domain. So you can use the Gaussian process after you unfold an image into a time series where you have sky pixels. It can be very unevenly sampled, and use the Gaussian process to interpolate over the science pixels that you want to estimate the 1 over f noise under. So this can potentially subtract some higher frequency modes that just a row by row subtraction cannot. So here's an example on a bright target of the time series. You can see with this GROBA, I call it for Gaussian process version of ROBA, and it can get you can reduce the scatter and the light curve. The gains here are more marginal. I found about 11% smaller noise with this algorithm over the pretty simple median subtraction row by row. So that's some of the things you can do with 1 over f noise, and that's an ongoing project. I look forward to that group discussion later in this week. Another thing, another kind of systematic that you can see with time series are wavefront variations. So this is using the NearCam short wavelength defocus imaging to do a phase retrieval. So this is a movie made by Randall Telfer during one of a exoplanet eclipse observations. And you can see the wavefront variations. There was a small tilt event during this. These are really, it's an incredibly sensitive technique that can sense these small. These are just a few, sometimes fractions of a nanometer variations in the wavefront that can be sensed with the defocused image. So a potential additional product that could be provided with the pipeline are some vectors that come from this defocused imaging. So this is what a series of images look like for the defocused PSF with a weak lens. And you can do a subtraction of these and see, for example, a tilt event that happened. Those were more common in the early part of the mission. Fortunately, the frequency seems to be going down. But you can do principal component analysis and find and essentially reduce the number of dimensions of all of those images to identify some modes is a very simple analysis to do. That's that's easier than these phase retrievals. And so some of these modes, for example, the red curve here shows the instrument electronic compartment heater oscillations with a 3 plus change frequency. And so these vectors can be used to decorrelate some of the systematics in a time series. Here I've shown a time series where with a very small aperture, which is more sensitive to these waveform variation, but also tends to do better in terms of 1/f noise for this mode. So a linear combination of these principal component analysis could be used to decorrelate some of these systematics in the time series. Another systematic noise monster are these visit long trends. You can see in time series. I've seen this in near spec and near cam. It's most noticeable when we're looking at a very bright target. So where both you have the high precision to see this and also it seems to be a larger effect. And it's more than just linear slope at times. There's some curvature to it. And after digging through the engineering database, there was a mnemonic that seems to have a similar shape, which is the focal plane array housing temperature. And so if you just flip it around in PowerPoint, you can see that these line up very well. This is a correlation, not necessarily a causation, but still potentially can be used to decorrelate the systematic. So here's a handful of observations that were done, and this focal plane array housing temperature deviation. And if you instead of just measuring the absolute temperature, do a differential temperature, you can see this anti-correlation between flux and the focal plane array housing temperature. So this is potentially can be used as a detrending vector as an alternative to what's often used as a polynomial for the trend. And then I have just a random side that I think would be nice to have is a tool to analyze the data quality. So this can be hard to read, interpret in your head, and DS9, unfortunately, is always about 1 digit short of what we want to see for the full number of these data qualities. I did write a very simple 20-line piece of code to just print this table, probably going to be in 1 line by a better programmer, but just to take that number and turn it in to a table for what these data quality pixels, and so it'd be nice if there's a tool out there to just make this easier, or maybe and I see there's some discussion for JWST to make this possible. So back to the main part of this odyssey in combating these noise monsters. With 1/f noise, ROBA algorithm can mitigate this noise and also has better interaction with other steps like the jump step in the pipeline. Doing some fancier methods can slightly improve upon the 1/f noise subtraction. So we can use principal component analysis on the defocus data to provide some detrending vectors. And then also we find this anti-correlation with the focal plane array housing temperature and the flux that can be used to decorrelate some of these visit long trends. So thank you for your attention, and I'll take any questions at this time.
Yes, I know. All right, thanks so much. Let's see, there are a couple questions, both from me, I think. One of them is the focal plane assembly temperature you refer to, that's the near cam focal plane that is the temperature is being measured for?
Yeah, yeah, and it's kind of bizarre. Like the temperature monitor on the detector seems to be very flat. It's this the housing that surrounds it shows a trend. So it's possible, maybe that the thermometer that's on the detector is not sensing everything we want.
Yeah,
Or it's possible it's just a correlation and not a causation. They
right.
seem to line up.
And then the second question is the IEC heater thing you showed with the higher frequency stuff. I'm pretty sure I know the answer to this, but is that mnemonic available in the engineering database or the relevant mnemonic?
Can you repeat the
The IEC heater mnemonic, the higher frequency correlation you
I
showed?
think I haven't heard the latest on whether. So what I did was just on images, but maybe one of the Wavefront people there can comment on whether that is now available
Yeah.
in the database.
If you could do me a favor and reply to my question saying something like, not that you're aware of or something like that, we can keep moving forward on that. Do you know which mnemonics are preferred there, or did somebody give you that stuff? If you know which
So
mnemonics
what
are, yeah, go ahead.
I didn't actually explore. I didn't actually yet plot out those mnemonics, but we know from the frequency and other analyses that those oscillations are the IEC heaters.
Gotcha. Okay. Yeah, I'm fishing to figure out what we need to get in the engineering database. So anybody that wants to help me with that, please go ahead and comment on my question. Thank you. Let's see, and that's it. We're going to move on. Thank you very much, Everett. And we're going to move on to Drake.
Okay, I'm actually going to use the laser pointer because I have arrows on my slides and if I use the cursor, I'm likely to reformat the disk accidentally. So I want to talk about this is the result from a cycle 1 calibration program, and I'd like to acknowledge my collaborators most of them are members of the MIRI instrument team, and particularly Tom Green, who actually suggested that I do this kind of observation. And this is observations of a bright eclipsing binary star. It's a visual magnitude 5.7, so it's probably one of the brightest sources ever observed by MIRI. And we want to use MRS for exoplanet transits. And the reason we look at a bright source is because we want very low photon noise, so we can see all the instrument systematic effects that are going to be a problem when we observe a bright transiting planet system. And one of the motivations was about 5 years ago, Ignas Snellen and his collaborators suggested that MIRI MRS could be used to detect carbon dioxide in the atmosphere. There's a temperate exoplanet that was discovered by radial velocity orbiting Proxima Centauri b. It's the closest habitable planet to the Earth. It does not transit, but nevertheless you could use MRS as its lines move in radial velocity. You could do a phase correlation and extract its spectrum with MRS data. So to sort of see whether that works and to look at a bright source, we decided to look at R Canis Majoris. It's a bright, semi-detached eclipsing binary. And the reason we pick an eclipsing binary is that stars have simple spectra. We want to start with something where we sort of know the answer. We're not going to start with a planet where the spectrum might be very complicated and we don't know whether we're seeing an instrument effect or a planet spectrum. Here we're going to start with stars, and we sort of know what to expect from stars. This is a binary that fills its Roche lobe. The secondary is an extended source. And we're going to look at its secondary eclipse. Now this is bright, so it produces a lot of data. We have 30 groups per integration, about 400 integrations. And because of data volume, we had to divide the observations into an ingress, starting before eclipse and then ending during the middle of eclipse, and then egress, which was observed 18 days later, starting during eclipse and following it to after eclipse. Now, when we got the data, whenever I get JWST data, I'm very excited, and I go right to the rate-ints images. And I saw, marked by the arrow here, that there were a lot of pixels where the pipeline gave me not a number, the dreaded not a number. And I thought, well, I've got to do something about that. So I went through various, I thought I'm going to have to go in at the group level and look at the data and see what exactly is happening here. And I did. And in various ways, I produced different versions of radiance that I call Drake-ints. And now, it's easy. It's actually easy to do that. You can just go into to one of the last groups, not the last group, but maybe next to the last group, and subtract the first group from the last group, and you'll get something that looks nice, but it's not necessarily going to give you good spectra because it's not necessarily correct. So I've gone through a couple of different ways of doing this, and in the end, I'm going to use something that doesn't really use the equivalent of a radiance file. I'll explain it to you what I do. But when I started looking at the ramps, I saw some things that really puzzled me. Here's one pixel. This is one of the bright pixels in channel 1. So this is a short wavelength where the star is mucho bright. And the black points are before ingress, and the blue points are the same pixel several hours later. And you see there's this drop down, which I guess I don't have an arrow on it, but it's obvious, should be obvious to everyone looking at it. There's this discontinuity in the ramp. And the same pixel, it happens several hours later, but at a different group number. So it's not a cosmic ray hit because it's not a random thing, and I would expect that most discontinuities due to cosmic rays would be increases. In these data from this calibration program, most of the discontinuities in the ramp are drop downs rather than jump ups. Now, yeah, this is close to saturation. So I said, okay, that's cool. So it's close to saturation. I'm not going to worry about it so much. But here's another pixel. This is in data numbers. This is nowhere near saturation. And you can see here, it doesn't drop down, but it just like flattens. And here's another one where it actually does drop down a little bit. Still nowhere near saturation. We have 400 integrations, 30 groups per integration, and of course there are like 1,000 pixels in the spatial stripe on the. So there are many thousands of examples, but I could make 1,000 plots like this. These are very common, and most often we see drop downs rather than jump ups. There's a few jump ups from cosmic rays, but mostly it's drop downs. And because the source is very bright, the signal to noise the photon limited signal to noise is very high. So it's easy to see these. But I think if the source were fainter, these would be below the photon noise and the pipeline wouldn't notice it. So, okay. Now, here's the brighter, fatter effect. And I was expecting to see it in the data, but this was a little startling nevertheless. With such a bright source, there's really strong contrast between, this is a pixel adjacent to the brightest part of the spectrum. And you can see it starts out in a nice slow slope, and all of a sudden the slope increases tremendously as it gets electrons from an adjacent pixel, and then it ends up okay. But you know, there's no way I can fit anything to that. It would probably require an 8th order polynomial, and I'm not even sure what those terms would mean. So how am I going to analyze this? So what I end up doing, I've analyzed the first 3 channels. There's channel 4 way out at long wavelengths, and the star is not very bright there. So for now, I haven't analyzed channel 4, but I've analyzed channels 1, 2, and 3. Channel 1 is the brightest, so it's the hardest to do. So what I do is, first of all, I subtract the first group, I divide by the flat. And then at each group, I go in, at each group, I co-add about 20 exactly 20 columns, row by row. In other words, wavelength by wavelength, I go in and add 20 columns at each group, centered on the spectrum. And that's intended to capture all those brighter, fatter electrons that got transferred to other pixels. Now, yeah, they get transferred in wavelength too, but the variations in the spectrum with wavelength are not so drastic, so they get shuffled back and forth, and it just kind of smears out the spectral resolution. That's the least of my problems for now. So I add spatially. Then I construct Then I make a ramp out of those sums. I first take the time derivative, because remember, in my one ramp, it was just a little flat spot, which in the ramp itself isn't very noticeable, but in the derivative, in the group-to-group differences, it's a big dropout. So I take the time derivative, and then I have a running median filter that looks for deviations and compares it to the Poisson noise from photons and corrects the derivative, then reintegrates and makes the ramp anew. That corrects the ramp. And then I fit a quadratic to it and extract the linear term like normally. Then I want a spectrum ultimately, but so I've got an eclipse shape, which for these contact eclipsing binaries, who knows what the eclipse shape is? It's some complicated thing having to do with a Roche lobe. So I first sum all the wavelengths and make a white light eclipse, and then I scale that at every wavelength to get the wavelength to wavelength differences. So I get the individual wavelengths by scaling the white light eclipse, and I'll show you the white light eclipse. Well, the other thing that I investigated was the fringing. There's fringing in MIRI, and it's optical fringing, and since we have ingress and egress 18 days apart, it's really interesting to ask, is the fringing stable over 18 days? Here's the channel 1 fringing, and ingress and egress, I had to offset them slightly because they would lay on top of one another in terms of flux. So I've offset them slightly, and then I ratioed them. And they don't, the fringing doesn't move in wavelength, but when I ratio, there's a structure there that I don't understand right now. And maybe it has to do with the brighter, fatter effect, or there's another suggestion that I'll make at the end that may cause it. But at longer wavelengths, channel 3, the ingress-egress fringes, if I ratio them, I get something that's generally less than 1%. They're pretty stable at long wavelengths. And I think they're optically probably stable at short wavelengths, but I'm probably not really removing all the brighter, fatter, and nonlinearity effects yet. Okay, so what I do in channels 2 and 3 is very similar, except I can't just add the pixels spatially, because at these longer wavelengths now there's thermal background. Even though this is a 5th magnitude star, long wavelengths, there's thermal background, and I don't want to just add that background noise. I want to discriminate it. I want to subtract the background. So what I do is I do a optimal extraction, a profile, the spatial weight by the spatial profile using the Horn prescription. That effectively averages pixels in spatially. So I'm adding up some brighter, fatter electrons, not explicitly, but by using the profile, I'm adding them implicitly, and the brighter, fatter effect isn't as important at these wavelengths. Then, as before, I construct the time derivative, median filter it, and integrate it, and do as before, and get white light eclipse curves. Here are my white light eclipse curves for the 3 bands, channel 1, channel 2, channel 3. I've offset them vertically, otherwise they would lay on top of one another, and I normalize them to unity for the median value out of eclipse. And I applied the same normalization to ingress and egress, and I didn't change anything else. So it's just the data 18 days apart, with the same normalization factor. You can see JWST is very wonderful. If you're online late, and you can see 2 curves that almost overlap, and that's just the difference in the sensitivity of the detectors and so forth over those 18 days. I didn't try to take anything out. And there's a few dropouts. You see some spikes. I didn't try to take those out. Those are in the day. With more care, I could filter them out. But this is the secondary eclipse. There's more noise in channel 1. There should be less noise in channel 1 because there's more photons. So I've got more work to do there. But channels 2 and 3 look really smooth. And if I do the wavelength, the scaling with wavelength, for example, at 12 microns, there's this spike. And the spike occurs, I'm confident this is a real effect in the secondary component of this eclipsing binary, and it coincides to the n=7 to n=6 transition in hydrogen, in atomic hydrogen. And it's probably formed by recombination because there's a lot of gas and it's hot. And solar-type stars, the sun has emission, not in the hydrogen line, but in a high Rydberg emission line due to magnesium, which is at a nearby wavelength. And that's in the upper photosphere of the sun. And in the sun, the hydrogen is in absorption because it's formed deeper. Here, the hydrogen is probably formed in a much more extended cloud, and we're seeing recombination. And we don't have enough optical depth in magnesium to see emission in magnesium. There's other structure here that I'm not certain is real yet. I still want to do more work on the data analysis. Okay, so there's a prominent brighter, fatter effect in these data. It's mysterious to me why most of the discontinuities in the ramp are drop downs. Please, somebody tell me why. The only reason I can think of maybe is there's some kind of electronic crosstalk. We're putting a lot of photons on this detector. We're generating a lot of electrons. And maybe then when a cosmic ray hits another part of the detector, it causes the voltages to move around a little bit and gives me drop downs. So it's helpful to co-add all the pixels at the group level. And for these high signal to noise ramps, a more aggressive filtering of the ramp I find to be really pretty necessary. The fringes, the optical fringes, are almost stable over the 18-day interval. The channel 1 fringes, there's this low spatial frequency structure when I ratio them. I suspect I'll ultimately be able to remove it. I don't think it's optical. And optical extraction at the group levels is mostly successful for channels 2 and 3. I'm still working on towards better results on channel 1, and one of the main reasons I don't probably have good results on channel 1 yet is this is an integral field spectrometer, and I'm only working so far with the brightest spatial stripe. And Guanwei Fu, my former student, has demonstrated to me that if you add different spatial stripes in the integral field, due to small jitter from JWST, there's noise that cancels out. You move, the telescope moves slightly in one direction, and one stripe gets fainter and the other stripe gets brighter, and the flat fielding is not perfect and it makes noise. So I think, I'm hopeful that I can make channel 1 behave by the next stage in this is to co-add different spatial stripes. And I'll stop there. Thank you.
Awesome. Thank you very much. So we have a couple comments. One, Taylor Bell says maybe they see the same thing with the LRS in terms of the downward step thing. So it's not just.
I haven't looked at the LRS at the group level, but they see the same thing. Oh, that makes sense. It's the detector, right?
Exactly.
The detector doesn't know what the spectral resolution is.
Right, and then Mike here left a cryptic comment saying he might be able to explain it, but he doesn't say. So I'm going to hand him the microphone. We're going to see what happens.
So the key thing in MIRI that's different from the near infrared is when you hit hard saturation, which is way above where we flag saturation, the pixel no longer spills charge to its neighbors. Instead, it becomes a sink. And so that's why you see these rough increases in slopes after a neighbor pixel hits hard sat. So it could be that something like the one where you showed it ramping up and then getting normal. It got normal because its neighbor hit hard saturation. And so then the two matched. And something like that could be what's happening with your big jump down. That if all of a sudden there's a super bright.
Okay, so the good news then would be for an exoplanet transit. There isn't an exoplanet transit star that's this bright. Some are close, but not quite this bright, and so the whole problem might go away or at least a lot of it might go away.
So the problem with that is to remember that if we hit hard sat on the pixels, then they stop spilling into neighbors and charge is no longer conserved. We have no idea.
So where does the charge go? Or
right through
to
the mucks down below.
Okay.
All right, that was exciting. Mike, if you could put a subset of that or that into the comment for posterity, then we can come back and give you credit or assign blame if the explanation turns out to be right or wrong. So, all right. Next up is Nestor. Nestor's online. No, Nestor's in person.
Yeah, you might want the microphone. Yeah.
tough spot, second to last. That's gonna be, and we'll try to wake you folks up. I promise you it's exciting, it's interesting too.
By the way, if you all read the general channel in Slack, or if you just heard from me now, there's a weekly beer thing in the cafe that starts as soon as you leave the room here. And it's $3 a beer, and so you're all invited if you're interested after you leave this room.
All right, with those beers as excitement, thank you for bringing that right now. I'm gonna go to this part, which is improving TSO sampling cadence and precision by correlated double sampling. Probably a lot of these words are very new to most of you folks. So I promise you, by the end of this talk, you will understand every little word that is on here. The first one, that actually doesn't need a lot of introduction, is, I don't know what's going on. There you go, fun. All right, it's time series observations, right? And Space Telescope, we love acronyms, so that's why I'm gonna try to not use them. I failed, of course, from the beginning, but still. So let me tell you a little bit of how time series observations work. You've seen some of that already, right, through the previous talks. But I'm gonna walk you through, a typical day on a TSO world, right? Like my day, David Green's day, Drake's, Loic, etc. There's many people here, Taylor, that do a lot of TSOs, and this is more or less how it goes. So first of all, what is a time series observation? Let's start with the basics. This is multi-integration exposures, right? So you have an integration, have several groups in the integration, and then you cover all of them, and that's kind of the definition. And typically, you're trying to follow this time variable phenomena like transit in exoplanets. This is not the only time series science case, but it is the most popular. So that's why I'm going to make the example that I'm going to make in this talk are going to be based on transit in exoplanets, actually, because that's also what I work on. So how would a typical day on a TSO world will go? So you get your data, you're super happy, and then you look at the uncalibrated data and you complain, right? Because the data doesn't look that nice from the the products, like the raw products. But then you marvelous folks, you know how to reduce this. There's a pipeline, right? And then some magic happens in detector one, and you get happiness, right? You remove this 1/f noise, different degrees, and so on, and you're much more happy. Then what happens is that then you go, and then for each pixel, you look at each integration at each pixel, and then you have these up-the-rim samples, right? So Drake was just showing these beautiful plots, and you were seeing counts as a function of the number of groups. And then what you typically do is that you go here and you measure some sort of slope. So Drake, for instance, was using this quadratic term and using maybe one of those terms to measure the little slope. You get your beautiful slope, and that's it. And in transits, for instance, what you do, especially in the near infrared, which is much more easier in that regard to get to this stage, what you do is that you capture your slopes on the different integrations, and you just plot them. And you plot those slopes, and you get these beautiful transits that, they made press releases and everything. This is one example from WASP 96b, in which you see the transit of the exoplanet beautifully centered around, and everything is great, right? So the point that I'm trying to make today is that there's an alternative to this series of steps. And there's a reason for doing those alternatives. And that has to do with some caveats with slopes and TSO. So there's at least two issues with working with slopes. The first one is more of a methodological one, which has to do with the fact that binning is thinning, right? When you're fitting a slope, you're binning groups between them. Interesting thing is that if you go to your favorite light curve generator, whether you're measuring like supernovae or transits or whatever, these things model instantaneous fluxes. But what you're measuring in the slope, it's an actual slope. You're binning all the groups together. You're not measuring actual instantaneous fluxes. Actually, you can showcase that measuring slopes and measuring instantaneous flux are different, and they can give rise to some important offsets. I'm not going to tell you the planet. If you're interested in which planet this is it, I can tell you later. But this is an actual simulation and a real observation strategy, in which if you compare noiseless slopes, like you compute your fluxes and then you feed slopes to noiseless data, and you compare that against like the instantaneous flux models of a transit, you get an offset which is in the order of like 200, can be up to 200 ppm. And that's That's a lot. Like you can actually measure that from light curves. Okay, that's one thing. So be careful when you're fitting slopes, right? And the second one is that slopes actually hamper kind of the raw cadence that JWST has. To give you an example, let's go back again to this WASP-96B transit. So if you do a close-up here to these different integrations, the slopes that happen here, they take like 80 seconds in between. But the group time is like 5 seconds for nearest us. So you want to really take advantage of those 5-second integrations, because, sorry, that's 5-second cadence, because there's a lot of science that you can do with that. There's transit and exoplanet science that depends on very high cadence, and there's also stellar astrophysics that you can do, like pulsations at this level of detail that are super cool. It would be great if you could, harness, or harvest is the word, I think, that group level cadence. And that's where the second name in the talk comes in, is correlated double sampling. So you will learn TSOs, you'll learn sampling cadence, and you'll learn precision. Now I'm going to go into correlated double sampling. When I arrived at the institute, I kind of had this idea in my mind, and I can mention it to people, and no one understood me until I learned this magical word, and then everyone was agreeing with me. Correlated double sampling is just a fancy way of saying, let's just take like group N and subtract it to group N minus 1. That's it. So you have this up the ramp sample, and then you just take like group 2 minus 1, and you get like an offset there, because there's a rate, say 100 counts. And then you take 3 minus 2, and in theory, those should be constant rates. Like that's what we are believing when we're fitting slopes, right? And then if you take those group differences, then instead of working with the group's influences, you can work with the group differences. Now, the word correlated, it's important because these samples are correlated, because you're using, in this case, I'm using, for example, in the first 2 differences, I'm using group 2 times, right? But I'm harvesting that cadence. Now, you can actually show that correlation, if you assume that your detector is just read noise plus Poisson, like a Poisson process with noise, you can show actually the exact form of that covariance matrix between the correlation. Actually, it looks something like this. Like this is the covariance matrix between subsequent correlated double samples. This is known from the 90s or 80s, like from Fowler himself. And the covariance is actually given by the read noise. So the more read noise you have, the more the correlated double sample, the more correlated the correlated double samples are. So if you're in a situation in which you have like a lot of photons and little red noise, that's perfect, because you can just use this thing and the correlation basically vanishes. I'm going to showcase that that's actually the case for most time series observations. So let me show you some simulations on correlated double samples. I have to give a huge shout out to Mike Regan here, who helped me. I bugged him for like weeks trying to understand this thing, and Mike is laughing because I was like in Slack, and and he taught me all he knows basically on this part, right? I think. So I generated some simulations. And what you're seeing as little points here are these correlated double samples. And in big blue points, what you're seeing is the average of those on each integration. So that's what I'm going to put here. And what I want to do is to compare that you compare those against the red dots. You cannot see the red dots. That's actually a feature of this plot, not a bug. The red dots are actually matching, and the red dots are actually the ramps. So I generated this up the ramp sampling. I fitted slopes. And then with that same thing, I generated the correlated double samples. I generated the average of that. And then I plotted the time series of this. So it's integration versus like rates or correlated double samples. And they're basically the same. And the properties that I use to generate these simulations are very similar to what you see in classic time series observations, actually. I repeated this experiment for a wide range of read noises and a wide range of rates. And the thing to take out of this is that the color tells you how much better slope fitting is with respect to these average correlated double samples. And what you want for this is to be very bright. So here's the low signal to noise ratio regime, in which you have like large read noise and low rates. So you're dominated by read noise. And as I told you before, that's where the covariance from those correlated double samples really matters, and it kills you, right? So correlated double sample on this edge is really bad. You don't want to use that, probably not unweighted as I was doing it here. You want to use slopes. But in this other regime, in this high signal to noise ratio regime, like fair game. You can use that, and then you will be fine. Interestingly, that's like the region in which most of JWST time series observations live. And that's great, because then you can harness the power of correlated double samples. All right. Once I did these simulations, I like convinced myself I'm gonna try this thing on real data, right? And I was like, this is gonna work, it's gonna be so nice because, I mean, it works in simulations. Why is it not gonna work in data, right? Fatal flaw, typically. Famous last words. So here's the transit I was showing you before with REMS, right? I already showed you this. This is what it's published out there. And what I'm gonna show you next is the correlated double sample light curve, right? Are you ready to see this marvelous thing? It's horrendous. If you just take it, this is like the linearity corrected data. So I took the correlated double samples. Here's the interesting part though. When you take a good look at, like if I do a close-up to this light curve, well, first of all, you can still see the transit, which is great. But if I take a close look at this, I'm gonna do a close-up. You can see that the correlated double sample, I'm plotting the correlated double samples for each integration, and they're very repeatable with each other, right? They are like it's the same thing over and over again. Actually, and this is what I'm going to show next, if you just put them all together on top of each other, they all line up super nicely. So this offset in correlated double samples, so you remember that I gave you, like I told you, like this thing should be constant. It's clearly not. So the CDS are clearly not constant, but they're remarkably repeatable. So what you're seeing here is a combination, I think, between nonlinearity offsets and charge migration. This is in the near infrared, by the way. This is near source. And because it is so repeatable, you can just model this thing directly. You can self-calibrate your data for time series observations. This is hard to do for absolute flux calibration, but with time series observations for transits, you're typically more worried on the relative flux. So that's okay for you. So actually, you can use this self-calibration and then apply it back in the data. And this gets more or less very well correct. So this is the uncorrected one. And then when I apply the correction, this looks like this. Pretty nice, right? And then when you do the same thing on the whole transit, this is the uncorrected CDS. And this is the correct one. So you get back down. And after if you bin down, you get a slightly better precision than the actual slope fitting, which is great. There's, so the thing works, right? There's many other benefits that I would like to mention, and I could go for hours. Like for instance, corrected for this 1/f noise is much easier on correlated double samples because you remove any bias offset or any jumps in between, which is great. So it has many benefits to work with that we're still working on exploring. But at least like I wanted to bring to you folks that this is like an alternative to doing the normal slope fitting as well. You can compare both. You can see how it works for your science case. But for us in transient exoplanet science, it's working super nicely. And that's basically what I wanted to show here. So, bit of a summary on this. So first, yes, RAM fitting works fine and works beautifully for most data sets. But what can improve in terms of precision and cadence by using group level counts directly. I wanted to make a highlight here on precision. I'm not saying like CDS is better than slopes. What I'm saying is that for some applications like transit and exoplanets, there's some data sets for which this binning and this sinning thing comes into place. You might want to be careful with that. And then doing CDS, it's actually an easier way to bypass that and get like similar precision, or better for some science cases, or can it enable some science cases even. This can be done via correlated double sampling. It's not the only way of doing this, of course, but this is one way of doing this. This produces correlated samples, but in the high signal to noise ratio regime, which is applicable to some TSOs, the covariance almost vanishes, which is cool. Actually, you can actually take that covariance and apply it directly because you know the formulation of it. So you can apply it in your data directly, but that's much more cumbersome. And one detail is that KMR will be taken as nonlinearity residuals and or charge migration and or something else that I'm not mentioning and that maybe Mike Regan and some other folks will figure out and tell me about it, is seen as those CDS groups. So the correlated double samples are not flat. This is, however, remarkably repeatable and can be corrected using the data itself. So you can do like self-calibration, which is great. That's it. Very simple talk. Thank you.
Very nice. Shall I channel Mike or hand the microphone to Mike?
Yes,
Hand the microphone to Mike.
And there's one way is also.
Okay, I'll be back there in a moment.
So the reason you're getting the error at 0 at the low flux in the nonlinearity correction is because we force our nonlinearity correction to be 1 at 0 counts, and we're really not at 0. Miri's highest error is also at very low charge, which should be the least error. And if you let the linear term float, that error goes away.
Right.
But most people don't care because it's such a, you're at 0.004.
Right.
But here, it matters.
Yeah, we like the percentages in transits, right? Yes. Yeah, fair enough. Good point. Thank you, Mike.
Hi, my name is Guang Wei. I'm a postdoc at Johns Hopkins. So I have been doing exactly the same thing for mirror MRS. So one thing I noticed is the ramp is not consistent between in and out of transit because your flux drops by 2% in transit. So when I do that, I get the group number dependent transit depth. If I fit the transit liker for each group number. So for example, if you go back your slide, I think for your example, you have about 12 groups. So if you fit a transit liker for each group, I would be curious to see if they have all produce the same transit depth, because for mirror,
Without correcting for this?
Yeah, without correcting.
Yeah, of course. Yes, yes. You will get a different transit depth for sure. Yeah, because you have like a,
Why?
0.5%. Because
but
you're,
this is relative, right?
yes, but still, it still enters into the equation, right? You can show that if you have a miscalculation, I think Mike did this work actually. If you have a miscalculation in the nonlinearity correction, then the relative flux will change in itself as well. Very tiny amount, but that tiny amount depends on the actual transit depth and transit duration and so on. So I'm actually not that surprised to see that. But actually, that's why I corrected it. I see the same thing here. If I don't correct for this, which I do, I self-correct against the data itself, I do see variations in the group level for sure. But if I correct it like this, and then in the CDS liker that I showed here, and I feed the transit model to this one, I get virtually the same precision, slightly better than the time of transit center for WASP 96B. So you need to correct for this before doing that, I think.
All right, that was enough to whet people's appetite.
Fair enough.
Yeah, we're in jeopardy here that the chairman likes this topic a lot, so I have to rein myself in too. So, all right.
Thank you.
We have one more scheduled talk online. Timothy Brandt, who I see. We're bringing up your. Oh, no, we're not. You're going to share. There we go. Yeah.
Up to you. Is this good?
Sound is good. We are. Yes, that looks great.
Okay, excellent. Thank you. I apologize I couldn't come in person, but I'll make it up by coming for a longer stay in January. So I'll be talking about how you combine your samples up the ramp, and this is going to end up leading naturally into a new jump detection algorithm. So it's a generalization rethinking of a substantial fraction of stage 1 of the pipeline. I have applied it to data, and I'll be interested in looking at it in more detail with various data sets. There's a lot of math that is in that archive paper. There's also a code implementation here, so if you want to try it out, you can do so. It's not a daunting amount of code. So I'm very fortunate to go after Nestor's talk because it's a related topic. You want to fit a slope to the sequence of reads, and Nestor was in the high signal-to-noise case where the adjacent differences in reads were more or less decoupled. So I'm going to assume the general case where they are not, and we want to fit a line to this. So for a well-behaved detector, you can write down chi-squared, run to minimize chi-squared. The chi-squared that I've written here is a naive value for these different counts at each read. It's not quite what you want to minimize, though, for exactly the reason Nestor said. You couple these different reads together. In this formulation, it's photon noise that couples them together because a photon that shows up in the first read is also there in the last read. And so this covariance matrix will depend on the photon rate and the read noise. And importantly, the covariance matrix is different for each pixel. So this optimization of chi-squared is not the standard practice. It is not what is done in the pipeline. It's not what is currently planned to be done for Roman either. It's close to what is currently done is close to optimal, but not quite. The different reads are combined, but with weights that vary discontinuously. So the weights for each read, when you combine them together, depend on an estimated signal to noise, And because of this discontinuous change, you see this sawtooth pattern where the weights change your relative signal to noise changes by a little bit. You can see on the Y scale maybe that you're something like 1% off of the optimal rate, maybe as much as 2% depending on your readout mode and your signal to noise ratio. Another thing that I don't think has been appreciated is that this also introduces a bias in the data. Not a big one, but a real one. Because we're estimating the signal to noise ratio using the first and last reads. There is some covariance between that estimate and the slope that we get out at the end. If we're changing our weights, then we change that covariance. If we happen to be at a count rate that puts us at that threshold, it turns out that we're combining these two different covariances above and below the threshold. If we're over here, far from the threshold, then the mean in the y-coordinate is 0 because on average we don't have any error, we hope. And the mean in the x-coordinate in the inferred slope is also 0. But that symmetry breaks when you're near the threshold. And so you will have a net bias in your slope. And in case you're wondering, it's small, but you can calculate it exactly. This is what it is, for example, for 10 reads, 10 electron read noise. Where I'm talking about the read noise of an individual read now, not a correlated double sampling read. This is similar to the read noise that we actually see in JWST. So it's small, but it's real and it's calculable. And we can even see it in data. So this is from a near-cam ramp from some of the commissioning, I believe, where I'm taking the approach in the pipeline where these weights change discontinuously, and the vertical line shows where they change. And you can maybe see this little hump. It'll be a little clearer if I use weights that don't change at that boundary, then the hump goes away. So if we actually use the rate that we would want to use if we solve the problem using chi-squared, then we can make it go away, and that's what I'll be showing you as part of this. So the official rate.fits file does indeed have this bump, and the approach that I'm going to advocate does not. So this is a debiased chi-squared fit. I'll tell you what that means. So the reason why we don't just calculate minimize chi-squared and do everything exactly statistically correctly, assuming our statistical assumptions are valid, is because it's expensive. Because the covariance matrix is different for each pixel. Matrix inversion is messy. It's order n cubed. However, it turns out that if we play the same trick that Nestor did and we switch to looking at the differences between adjacent reads, the covariance matrix actually becomes tridiagonal. It's only neighboring read differences that are coupled together because the neighboring read differences share reads. But if you have two read differences that are widely separated, they share no photons, they share no reads, they have nothing to do with one another. And tridiagonal matrices are very special. It turns out that the inverse is analytic, and you can refactor your computations. So what had been naively n cubed to invert a matrix and get everything you want becomes of order n to invert a matrix and get everything you want. So suddenly this is not computationally expensive. It's order n. If I have 10 times as many reads, it just takes 10 times as long. And everything can be written in closed formulas. The math is in the paper, but the formulas in the end, they're not that daunting. There are ancillary benefits too. So we get the best fit count rate. We get the best fit reset value too. If you want to incorporate knowledge of the reset value for a pixel with a very high count rate, it's very straightforward to do so. You get your uncertainties and covariance for these quantities for free. And even better, you get chi-squared. So that is an immediate diagnostic to tell you whether your ramp fit was any good. A poor chi-squared tells you that your fit was bad, and this is a useful way of flagging data that I think could be implemented. Okay. That still leaves us needing to estimate the covariance matrix because the covariance matrix has read and photon noise. We might know the read noise more or less, but the photon noise is another matter. We have to estimate it. And depending on how we estimate it, that bias from earlier can return. Turns out, however, that if you just apply this approach twice, so you do your fit, you refine your estimate of the photon rate, you repeat your fit, so you double the computational cost, this bias goes away to first order. And I've verified empirically that it's at least an order of magnitude lower and no longer measurable. So With this approach, we can also remove the bias that is at a low level, but is in the ramps as they are now. Here's a plot of chi-squared, where the renoise that I had, I scaled it just a tiny bit from the published calibration file, but that looks very good. The chi-squared distribution that I would hope to see is the black line, and the one that I do see is the shaded blue region, and I can't tell the difference. So that's a really nice demonstration that in this case, the assumptions underlying our analysis of the noise look pretty good. Okay, here's an application to this actual NearCam data. This is the rate.fits file, and I'm going to blink it with a file that I have produced using this approach. So you might notice that the stripes, they're horizontal in this framing, the 1/f noise. They're a little bit different, but there are a few pixels here that you might pick out are treated a little differently. So the new approach might have a few fewer artifacts. And that's going to get to the second part of my talk, which is about jump detection, anomaly detection. Okay. And here's with no masking. Blink it one more time. Okay. So we get very small improvements, but improvements in signal to noise ratio. We get a goodness of fit metric, and we get no bias. We can also do a couple of other cool things, including hypothesis testing for jump detection. Right now, for the jump detection uses adjacent differences of reads, but it would be nice to use the whole ramp and see if the whole ramp really needs a jump, positive or negative, at some level. This is an idea of what you would be looking for, where this jump is not that large, and so it would be very difficult for a jump detection algorithm between adjacent reads to find this. Your eye can pick it out no problem, and that suggests that a statistical approach should also be able to pick this out pretty straightforwardly. So what I'm going to do for this is basically for every place there could be a jump, I'm going to hypothesize that maybe there is. And since I get chi-squared from my approach, I can ask, how much did my chi-squared improve when I hypothesized a jump? If it improved a lot, that suggests that there was a jump. If it improved very little, that suggests there wasn't. And I can apply a threshold on that based on whatever false positive threshold I want. And it's something that I can set. Okay. So the fact that the chi-square distribution governs all of these things means that the false positive threshold is something that you understand, assuming that your renoise that you're putting in is actually correct, and that you have nonlinearity under control and all of the usual things. Okay. Here's how that looks for different places where you might hypothesize a jump. This does not rise above the jump detection threshold for single differences, but you can see this large chi-squared improvement at the actual jump location. And so it can be flagged and robustly flagged. So here's the approach that I propose and that I have implemented, which is an iterative test for a jump at each potential resultant where it could happen. If there is something that's significant, flag it, and then repeat the process until you flag nothing more. A surprise for me was that I thought that this would be the cost of fitting a ramp, but you have to do that for each individual place where there could be a jump. So order n becomes order n squared. But it turns out that you're actually reusing so much of the computation that you've already done. You can refactor it to the point where it's still order n to test for a jump at every single location. So it's not actually expensive to test for jumps here. It's a fixed factor of a few beyond what you're paying to fit the ramp already. So it's not n to the fourth, which it would be naively. It's not even n squared. It remains order n with closed formulas and analytic formulas for your covariance and for your jump levels. So if you want to know what the jump levels were to model a snowball, for example, you can get them. They're available. Okay. Another interesting thing is that if a jump happens in the middle of a resultant, so you have read, 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 jump, read, read, and you average those together before downlinking it, then this can naturally combine those two possibilities. So you can search for jumps that happened within the resultant 2. And then you're masking 2 differences between this one, and between this one and this one, not simply 1 difference. For sensitivity comparisons, if we have 30 reads, this is a long ramp, but NearSpec has some ramps that are significantly longer than this, we can reach sensitivities that are about a factor of 2 better to jumps. So we can see very real and meaningful improvements over the single difference approach. It depends on where in the ramp the jump happened. You're most sensitive towards the middle of the ramp and least sensitive at the ends, where you don't have really the way of telling a slope for that second part so well. If you have a jump that happens within the resultant, it also depends on where within the resultant the jump happens. You're least sensitive toward the middle, but if you just take a single difference approach, you lose almost half your sensitivity if it happens in the middle, because now you can only check left or right, and each one is half of what it was. We still suffer a penalty, but it's a much smaller penalty if the jump happens in the middle. Here's what that penalty is in the single difference case, and in this case, assuming you have many reads per group. Okay, so the computational cost to all of this is pretty modest. I'm assuming here an H2RG with 10 resultants. Fitting a ramp takes of order a second on my old MacBook Air laptop. Doing everything, including iterative jump detection, takes maybe 5 or 10 seconds. I was playing around with NearSpec ramps earlier. Doing this with 60 reads, well, you just multiply all these numbers times 6. Again, everything is fully linear in the number of reads. Pure Python code here, there is nothing Python, JIT, anything. It can all be written as array operations calling NumPy, and so it's all closed formulas, it's all fast. There are a few hundred coding lines. I did make my own class, but there are tests built in, and so I think it's something that could be brought over to the JWST framework for a modest amount of effort, and I think it could offer real improvements. And I will leave it at that and take questions. Thank you.
So I think there's a question being typed in now. I will say we've already been looking at your stuff, and it's very impressive. It's hard to say no to better signal to noise and Oodle's better execution speed. So we're definitely interested in that. And the question is just to say great talk. So I think that's it. Thank you very much. I am going to, Marco, do you have anything, or shall I just close the session? All right. So I want to thank you all in the audience. You've been a fantastic audience. The talks were great. The commentary was great. It was just absolutely great having you here. I've been wandering the halls, and the folks here just love all the stuff that you guys have been sharing with us. I think it's really gonna help us. Make sure that happens. We will see some of you here tomorrow morning at 8 for 9, just 8 for breakfast and 9 here for the planning session. For those of you that are leaving, have a safe trip home. Thank you again for coming. There is, again, this happy hour thing going on, so you're all welcome to go there. And I'm going to close the first part of this conference now. So thank you.
Thank you.